Hello, my name is Marshall Lisenby, and this is Physics 2212 Lab 2 Charge Tape Revisited. The purpose of this lab is to compare the electric fields on a piece of tape from the point charge model to a new distribution model. So essentially, it's a continuation of Lab 1, but instead of treating the pieces of tape as a points charge, we're treating them as a line of distributed charges. Essentially, a bunch of point charges held closely together on a line, which we can evaluate as a whole. The materials are the same as the last lab, and we're still using LoScript as a computational model. And finally, as an overview, the result of this lab is that the Q from the point charge in the previous lab is 1.26 times 10 to the negative 8 coulombs, but now using the computational model of distributed charges, it's 2.47 times 10 to the negative 8 coulombs. Now, for the fundamental physics principles that are involved in this lab, and they are again the same as the last lab. We have Newton's second law, which is a system change momentum is proportional to the net force applied, or F equals ma. Coulomb's law, which says determines the force of attraction / repulsion between 2-point charges, with that equation there. And then gravitational force describes the attractive force between an object mass and the Earth, or F equals mg, which we know is opposite to the Coulomb's law here, especially when we use the distributed lines model, because they're equal and opposite on the piece of tape. So we have the same initial conditions as the first lab, with the length of the tape being 0.2 meters, the width being 0.02 meters, and then the U-tape mass being 0.002 kilograms. The experiment is the same, with tape B being the system and tape A, the marker boxes in the hands being the surroundings, and the measured distance being 0.027 meters between them when we notice the force being applied. And then here are the results from the computational model from Lab 1, and importantly is to highlight that the charge on the piece of tape is 1.26 times 10 to the negative 8 coulombs. So now we're going to do the same calculations as Lab 1, but account for the fact that we're treating the piece of tape as a distributed line of charges, or a rod of charges. So first we calculate the gravity acting on the piece of tape by using its mass times the gravitational constant, and then through Newton's law, knowing that Fg is equal to the magnitude of Fg is equal to the magnitude of Fe, so they're the same. And finally, we calculate Q through using the electric charge formula of a charged rod, which is shown right here on the bottom of the screen. And it's important that we know that the piece of tape is treated as a rod because it's a bunch of individual distributed charges across the length of the rod, which is in this, or length of the tape, which is in the shape of a rod. So we're able to use this equation in this model in this scenario. Now, for the computational model, we're starting with the constants right here as displayed. Getting into the meat of the computational model, we have two of our functions here. First, the electric field function, which is a continuation from Lab 1 and uses the electric field equation. The second is the line charge function, which essentially takes the length of the piece of tape and divides it up into n amounts of individual point charges. In my situation, I used 50 point charges for my piece of tape in this model, but it breaks them up and using a for loop builds an individual charge at each of those spots, evenly distributed across the length of the tape to create the full line of charge model. Now this is the big part of the computational model, the superposition, in which we use nested for loops to essentially calculate first, for each individual points charge in the top tape, we're going to calculate the electric fields coming from it from each individual point charge in the bottom tape, all 50 point charges. And then all of those, in effect, have an impact on the point charges in the top tape, and then when you sum them up, results in that net force and net field arrow acting on the point charge. So this is the meat that actually calculates the total field and force acting on each point charge within the top piece of tape using two nested for loops. Now for the results, you can see that the magnitude of the electric force was calculated to be about 3.15 times 10 to the negative 3, and the gravitational force was 1.96 times 10 to the negative 3. So a little bit of difference, but still very similar, which makes sense because they should be equal and opposite. And we can see the green arrows here are the electric fields. The white arrow is the electric force, and the yellow arrow is the gravitational force. And that's the completed GlowScript model for this experiment. Now for assumptions and errors. Some of the assumptions we made in this lab were that air resistance, friction, and tension from the boxes were all negligible. Assuming that each piece of tape had the same charge and that on those pieces of tape the charges were distributed evenly. And some of the errors could have been a loss of charge to the hand in the external environment, the net charge not actually being the same for the two tapes, the tension force not actually being negligible, and then imprecise measurements coming from the actual exercise of the experiment. Now for some discussion questions. What if you had modeled each of your tapes as a single point charge? Well, that's exactly what we did in Lab 1 with the first model. And we can compare that now to the new model with the line of charges model. And we can see the difference is that with the point charge is about 1.26 times 10 to the negative 8 coulombs, while with the line of charge is about 2.47 times 10 to the negative 8 coulombs, showing a clear and distinct difference. But why do these estimates differ? It has to do with different levels of precision in the calculation. The first model is incredibly general, treating the line of tape as a single point charge, while the second one is much more precise, breaking it down into a bunch of individual distributed point charges, which it is actually like in reality, which makes the second model and the second value much more closer to the real value just because it's much more precise and mimics the real situation a lot closer. So that's all for this lab report. Thank you so much, and I'll see you all next time.